In this video, I'm going to discuss contextuality and non-locality in Bohmian mechanics. And so I said in an earlier video that any hidden variables theory of quantum mechanics has to have contextuality. That's what the Kochen-Specker theorem tells us. And I'll talk about in later videos that Bell's inequality tells us that any quantum mechanical theory also has to be non-local. And therefore, if Bohmian mechanics is to be a candidate for an interpretation of quantum mechanics, it therefore has to be contextual and non-local. And so in this video, I'm going to show how Bohmian mechanics satisfies both of those things. And so the first thing we'll look at here is contextuality. And so let's consider an electron that's in a simple harmonic oscillator potential. And so in one dimensions that would look like this. And so this is actually similar to how the picture would look. This is just something I quickly put on Desmos, but it would look something like this, where this green here is our potential energy, and the red would look like the wave function right here. That's because this would be our wave function right here, where we see we have this e to the negative x squared over 4 sigma. And so it would look kind of like this right here. And so the width of it is this sigma here, and that's dependent on our angular frequency and the mass. So the energy eigenvalues are this, so dependent on the angular frequency. And so the wave function would look like this right here. So we have this, which is the Gaussian packet right here, and then this is our time evolution right here. And so this means that our phase is equal to this, which is in this exponent right here. And that does not depend on t. And so as I said in a previous video, the velocity of the particle is actually zero, meaning that it's stationary, it's not moving. And so, as I mentioned in a previous video, this entails that the momentum is equal to zero. But if a measurement of the momentum, so if we actually performed an experiment and measured the momentum, it's very unlikely that it's going to give us zero as the momentum. And so that seems to kind of pose a problem here, because this tells us that the particle is not moving, yet if we took a measurement, it would be moving, or the likelihood of it being moving would far outweigh the likelihood of it having a momentum of zero. And so we can see this because our Gaussian wave packet, if we use a Fourier transform to put it into the momenta, it can be written as a linear combination of the momentum eigenstates, where this right here is our momentum, and we see that this is another Gaussian. And in fact, when we do the Fourier transform of any Gaussian, it gives us another Gaussian. But the Gaussian will have a different width, essentially. And so, like, if we take this f of x here as our position, then we would get something like this as our momenta, where each position on this u-axis here is a different momentum. And so this is telling us the probability of getting a momentum at one of these places here. And so 0 is right in the middle, but we know that if we are going to try to get a momentum that's between some p and some very small distance away from that p, so the area under the curve in a very small slice here, such as right at 0, that the probability is going to be quite small. And so the fact that pilot wave theory predicts that the particle is not moving, but that it must have some probabilistic momentum, this appears to pose a problem for the theory. But in fact, pilot wave theory can give a correct predictions in the following way, using what is called a time of flight procedure for measuring the momentum. So this consists of turning off the potential that was confining the particle and allowing it to fly off in some direction to be measured at some location farther away from the starting position. So we can think of it like this. We have this electron that's just sitting still here, so its velocity is 0 at some position in this potential around our proton right here. So in this example, we're now looking at something that would be more three-dimensional, and so this would be our potential right here. So essentially just this Coulomb's law right here for our potential. But our velocity, as I said, is 0. Then we turn off the potential. So say this proton just suddenly becomes a neutron here. And so there is now no potential, but now this electron is going to fly off here. And so it now has some velocity. And so we know the mass of the electron because somebody has measured the mass of electrons. And so for the momentum, we need the mass and the velocity. But by this time of flight measurement, we can get the distance traveled in a given time. And so from that, we can get the velocity. So you can think of it like like the potential as being sort of like a slingshot that's pulled back. The particle is sitting in it unmoving when we are right here. Then upon releasing this slingshot at time t equals 0, so where the potential energy in the slingshot goes to 0, kind of like when we turn off this potential, the position so at time equals 0 and at position x of 0, the potential drops to 0 and the particle is sent flying. You then measure the position at some time t to get the velocity, which will give us our momentum here. So the differential equation for the position of a spreading Gaussian packet is this. So this is the differential equation. I'm not going to go into how to get the solution to this, but I'll just sort of hand this solution from down on high. So this is the solution. So this function here, this of position as a function of time, is going to be equal to all of this right here, where this x of 0 is the starting position. So this gives us what we saw in the previous video. So this figure right here, which we saw in the previous video. And so this is what that spreading Gaussian is going to look like, where we start with it right here, then it's going to spread out as it goes through space. And since we are letting the particle fly free for a relatively long time, we can get this right here for our function. And we could get this here by doing some algebraic manipulation. So just multiplying everything through by this h bar squared. So there'll be h bar squared here. Then this t squared here will end up being a lot larger than the h bar squared. And so we can just say that it looks kind of like this. And so if the particle is observed at some position at time t, we can infer the velocity like this. And so we started right here at x of 0, and we went up here to x of t, where we took the measurement of the position at some time, and so we get the velocity from that. And so according to pilot wave theory, the particle starting there at t equals 0, at x of 0 at t equals 0, will have a measured momentum of this right here after we cancel out the things that I have in red and blue. And so Norson says of this, and I'm going to quote him at length here, so this is kind of a lengthy quote right here, but the way he sort of talks about it is probably the best sort of way to talk about it. So he says, qualitatively, one sees how this particular method of measuring the momentum of the electron yields non-zero values, even though the electron's momentum was, just prior to the initiation of the measurement procedure, 0. And so he's talking about the method of measurement as the time of flight measurement method that I was just talking about. So turning off the confining potential energy changes the subsequent time evolution of the electron's wave function, which in turn causes the particle to acquire a non-zero momentum, or at least this is what happens if, as is overwhelmingly probable, the particle's initial position does not happen to be precisely, he used this symbol where I was using this x of 0 right here, but he's saying that we don't know to sort of arbitrary accuracy what the actual position, initial position of the particle was. The outcome of the measurement does indeed, in some sense, come into existence as a result of the measurement intervention. And so what he's saying by that is the particle's momentum was 0, but then when we started doing the measurement, we turned off that potential, and so that brought the momentum of the particle into existence. So our experiment itself actually brought that momentum into existence. but the process by which this occurs is clear and comprehensible and governed by the same quantum laws that, according to the pilot wave theory, always apply. What he means by clear and comprehensible is we can think about it in this way that I said, where it's almost like a slingshot, where we're turning off this potential and it starts flying. So there's not like some weird, mysterious, Copenhagen interpretation type thing of it, having and not having momentum at sort of the same time. He's saying that this is something comprehensible. This is sort of a common sense view of it. It almost seems too easy for us. We're used to quantum mechanics being this really complicated, weird, sort of, almost spooky, magical thing. And he's saying, this way of thinking about the momentum is, very clear and comprehensible. And I think, I mean, even for me, when it comes to like the Bohmian mechanics, it almost seems like kind of cheapening quantum mechanics in some way to think about it this way. But that's supposed to be one of the things about Bohmian mechanics or the pilot wave theory that is counted as something as a benefit for it. It's one of its merits is that it's something that actually makes sense to us. But anyway, to continue on, so Norson says this example nicely illustrates the point that for measurable quantities other than position, measurements according to the pilot wave theory do not just passively reveal the pre-existing value of the quantity in question. This is part of what is meant by saying that for pilot wave theory, properties like momentum and energy and spin and so on are contextual. And so, again, like I said in a previous video on the Kochen-Specker theorem, one of the things that any hidden variable theory of quantum mechanics has to have is this contextuality. And so Norson is here saying that Bohmian mechanics does in fact satisfy this contextuality stipulation that is put on any hidden variables theory. But this notion of contextuality, he says, goes a little bit deeper. It is not just that the results of a measurement of a certain property can in general be different from the pre-measurement value of that property. Rather, there may be no such meaningful thing as the pre-measurement value of that property at all. We have already suggested something along these lines in the case of the measurement of the energy of the particle in a box whose wave function is initially a superposition of several energy eigenstates. A complete description of the pre-measurement state of the particle in the box consists, according to the pilot wave theory, of the particle in a box wave function, so a superposition of several energy eigenstates, and the position x of the associated particle. It is simply not clear how, from these ingredients, one would construct from some specific energy value to attribute to the particle in the box as a pre-measurement value. And so he is going to be referring to this figure right here. In a previous video, I gave one that was similar to what we have on the left here, but this one also has this one on the right here that I wanted to use. And it comes from this 2016 paper here. And so the caption for this says that the left panel indicates the evolution of the wave function in configuration space, while the right panel indicates the evolution of the actual particle configuration for a random initial condition. And so we see that each of these different energy eigenstates here, so we have the ground state, the next excited state, the second excited state, and the third excited state here. And so when we do a measurement, these will go from being in a superposition to separating out from each other. And this is the path of the particle through configuration space. So that's the thing to keep in mind here, is that we are talking about configuration space. So we're not talking about actual like 3D real space. We're talking about a movement through configuration space. And if that doesn't make too much sense to you, I do have previous videos in this playlist, in this Foundations of Quantum Mechanics playlist, where I talk about what a configuration space is. But this is looking at the configuration space of or the particle in configuration space here. And we see this takes this complicated path as these things are separating. So we could think of these as both, uh, well, we can think of the end position of the particle here as sort of corresponding with, this place in our energy wave function configuration space right there. But anyway, to continue on here, but you might object, the pilot wave theory is deterministic. So surely the outcome of the energy measurement, so the final position here, so this is our pointer on our measuring device. So the final position of the y of t of the energy measuring apparatus pointer is determined by, i.e., is some complicated function of the initial states of the particle in a box and the pointer and the details captured by the interaction Hamiltonian of their interaction. That is true, but does not affect the overall point. The heart of the matter is that the measurement outcome depends not only on the initial state of the measured system and the initial state of the measuring apparatus, but also on the details pertaining to the specific way the measurement is carried out. And so this, again, is that contextuality that he's trying to establish here, that the Bohmian mechanics does actually satisfy the contextuality that the Kochen-Specker theorem says must be true of any hidden value, any hidden variables theory of quantum mechanics. So concretely, in our example, the measurement of the energy of the particle in a box, the outcome of the measurement will depend not only on the initial conditions, so the initial condition of the wave function, the position of the particle, and the position of the pointer, but also on the value lambda, which controls the strength of the particle in the box pointer interaction, and so determines, for example, the amount of time it takes for the configuration space of the islands. So he's talking about each of these gray areas here, which are the wave functions in this configuration space, and he calls each of those an island. So the amount of time it takes for the configuration space of islands described in the figure below to separate. From a purely dynamical point of view, it is hardly surprising that the configuration point, so this is the point after some time t, which after all moves in some complicated and erratic way while the islands are still in the process of separating. So this is that complicated and erratic way he's talking about right here, can end up in a different island depending on the amount of time it takes for them to separate. Remember, he said that the amount of time it takes for them to separate depends on how a measurement is actually being performed. So he says, but this means that the different and perfectly equally legitimate methods for measuring the energy of the particle in a box will yield different measurement outcomes, even if they are implemented on a perfectly identical system. Surely this demonstrates the complete pointlessness of trying to imagine that there is, according to the pilot wave theory, some pre-existing energy value which is revealed by, or even somehow affected by, and then revealed by the measurement procedure. And so he's saying that it's context dependent because it depends how you actually measure the energy, what sorts of results you will get from our experiment. And so this is taken as establishing the contextuality of the Bohmian mechanics. And so the next thing is the non-locality of Bohmian mechanics, which, as I said, is going to be something that Bell's inequality or Bell's theorem tells us has to be true. And so I haven't talked about Bell's inequality directly yet in this playlist. I do have a video on it earlier in the quantum mechanics playlist, which is just the sort of textbook quantum mechanics. And the reason I haven't gone over it yet, even though I'm kind of talking about it quite a bit actually throughout these videos, is because I am following Travis Norson's book called Foundations of Quantum Mechanics, and he doesn't do Bell's theorem until the chapter after the Bohmian mechanics, before he gets to the collapse theories and the many worlds theories, which I'll get to after the Bell's theorem videos. But anyway, so the reason I haven't gotten to Bell's theorem yet to actually talk about that in more detail is just because of the way that the book that I'm following is organized, and so I'm just kind of following that. But the important thing to know about Bell's inequality is just that it establishes that quantum mechanics, well, Bell's inequality plus the subsequent experiments that show that quantum mechanics does actually satisfy this Bell's inequality, show that quantum mechanics has to be non-local, or at least that it has to have no parameter independence, but I will get to that in future videos. So for now, we can just take the results at sort of face value and say that any quantum mechanical theory has to be non-local. And so this would also have to be true for Bohmian mechanics. And so that is what we're going to try to establish here, that Bohmian mechanics is in fact non-local. Right, so the velocity of a particle n at some instant depends on the instantaneous velocity of all other entangled particles. And so this is the velocity for each of these particles that is not particle n here. Say we have two entangled particles, which will have a joint wave function that looks like this. Then the velocity of particle 1 at time t is this. So this is just our guiding equation, remember. So we have this up here, which is our probability current, and then this down here is our probability density. And so it depends on the velocity is the probability current over the probability density, as we talked about in a previous video. And so we see that this here depends immediately. And so we're looking at this. So this is just for particle 1. So we have this position here for particle 2. And so we see that this depends immediately. So not on the speed of light. This is instantaneous on the position of particle 2 here, even if the second particle is arbitrarily far away. So this doesn't tell us that it has anything to do with how close the particle is, and that the interaction, or I guess the entanglement, is instantaneous. So let's think of two particle in a box subsystems that are arbitrarily far away from each other, of two entangled particles, and so we will get this wave function right here. This is our time evolution, but we see inside these square brackets that we have this linear combination for these particles. So we can have particle 1 at position 1 and particle 2 at position 2, or we can have particle 2 at position 1 and particle 1 at position 2 right here. And so this is our wave function here when we're in one dimension. And so this GIF right here is showing us what this is going to look like for a particle that is a superposition of two states, so the ground state and then the first excited state. And we see that inside this 1D box that this is sort of sloshing back and forth, this wave function right here. And so when we have a two-particle system, we're going to get this in 2 dimensions, which we will see down here. So this is what it looks like in 2 dimensions, where we can think of this and this and the pink here as being sort of these right here, where we have this sloshing up and down. So this would actually be the square of our wave function here, which tells us our probability. But if we want to think about just the probability amplitude, we could see that this would have sort of a amplitude on both sides. And so we can think of it sloshing upward in this left part before going down, and then sloshing upward in this right part before going down. It's sloshing upward here, going down, the sloshing upward here. And so we have this sort of going around in a circle that actually looks like this. So this is the configuration space shown here, but kind of showing how the sloshing is occurring. And so this is telling us the positions of particle 1 and particle 2 right here, and we see these are slightly out of phase, and so that's why we get this circular motion in phase space. So Norson says that the wave function psi in the velocity equation above. So this equation right here is an energy eigenstate of the two-particle in a box system, but turns out to have non-zero probability currents because of the relative phase between the two terms. And so that's what I was talking about. We're getting kind of a sloshing going around in a circle here in 2 dimensions. So kind of the 2-dimension version of what's going on in this GIF right here. So that is, it turns out that the two particles, according to the pilot wave theory, move in tandem as long as their joint wave function remains in this state. A density plot is shown in the figure below, so that's what this figure is here. I've adapted this one from what he has in the book, so the one he has in the book doesn't look exactly like this, but it looks pretty much like that. So as long as the two-particle in a box system remains undisturbed in the quantum state, so this is our quantum state here, the two particles each just continue oscillating back and forth in their respective boxes. So again, this is configuration space. And so the x-axis here is the particle in the first box, and the y-axis here is the particle in the other box. And so when I say that it's sort of sloshing around here, that's saying that that we have this going on in each box. So you'd have to think of looking at what's going on here, sort of looking at it from the x-axis position, and also here looking at it from the y-axis position. So that's how we get that sort of circular sloshing going on in configuration space here. All right, so if we have our old friends Alice and Bob, with Alice at box 1 and Bob at box 2, we could then have Bob measure his particle in box 2 using a pointer that starts in the ready state. So that's this phi of y here, which is a Gaussian centered at y equals 0. We then have this as our wave function. So this is still the same right here, but now we have this phi of y right here. So we have this as our interaction Hamiltonian, where we have this lambda right here, which is the strength of the interaction. And this couples the position of the pointer to the energy of particle 2. And so we get this. So we now have this phi right here, which is when it's showing up at, when it's sort of pointing at the value for energy 1. And this one here, where it's pointing at the value for energy 2. And so remember, this is Bob's measurement. So we're looking at particle 2 right here. And so what you can see from this equation here is that if this is telling us that we're at energy 2, that's talking about particle 2 right here, then it must be that particle 1 is also then determined by that, because it's this factor right here. And so that's going to be determined instantaneously by what the measurement on particle 2 is telling us. And so this requires a 3D configuration space, so I've just kind of laid flat this figure right here down on these 2 dimensions of our configuration space. Then the third dimension here, this y, is going to be our pointer. So when Bob measures his particle in box 2, the 2 superposed particle in a box states are lifted in the y direction in configuration space. The configuration point, which will have these coordinates, randomly ends up in one of the 2 separated islands, depending on the initial particle positions upon measurement. So what I mean by lifting is this. So this was our original state right here before the measurement. And then when we measure it, we can get either the y at the energy 1 right here, or we can get y at the energy 2 up here. So this, again, is adapted from a figure in Norson's book, and this is actually the description of his figure in the book. And so I will start reading from here. So prior to the measurement, the 2 superposed terms overlap in the y equals 0 plane. That's what's shown down here, giving rise to the wave function with the structure depicted earlier in figure 7.6. So this is the figure that, or this one is the figure that corresponded to figure 7.6 in his book. So that's why I put that down here or here. And so his figure 7.8 did not have this down here, and so that's why I adapted it for myself here. But the coupling to the measuring device's pointer caused the two terms to separate as shown here. So the particle 1 in state 1, particle 2 in state 2 terms. So particle 1 is in the ground state, and particle 2 is in the first excited state, is displaced in the y direction at a distance to energy 2, while this term right here, so particle 1 is in the first excited state and particle 2 is in the ground state, is displaced in the y direction by a smaller distance. And so that is these two positions right here in y. In the pilot wave theory, the actual configuration point will end up in one or the other of these two islands. So the islands being these two things here. So these two islands in configuration space, depending on the initial conditions of the three particles. So the three particles he's talking about is the particle in box 1, the particle in box 2, and the particle that corresponds to the measuring device. But then since the particle velocities depend only on the structure of the wave function near the actual configuration point, the subsequent evolution of all three particles will be dictated exclusively by just one of the two terms in the wave function. And this implies, among other things, that after the measurement on particle 2, particle 1 will stop moving. And so, I mean, that's kind of what he says here. So Norson says there are two ways to think about this. The first is that if y is equal to the energy 2 here, then we get this term. So remember, there were two terms in our wave function, and it will sort of become this one right here. But if we get the energy 1 in our y, then it will be this one right here. And so it is not in a superposition, and the motion of particle 1 is determined to be 0. The second way to think about it, so I'll quote Norson here again at some length. So prior to the measurement of particle 2's energy, the conditional wave function, and I put this in red because I'm going to talk about this in a little more detail down here. So the conditional wave function, which is essentially just the wave function of our system. So of particle 1 is the superposition of the ground state and first excited state wave functions, which gives rise to the oscillatory motion we saw earlier. So when I was talking about that sloshing around in our configuration space, that's the oscillatory motion that he's talking about. So after the measurement of particle 2's energy, the conditional wave function of particle 1 collapses. And I'm going to get into this a little bit more here in a bit, because one of the things that he has sort of talked about a bit is that we don't need the collapse postulate in Bohmian mechanics, but we do still, when we talk about the conditional wave function anyway, we do have collapses, but Norson will say that these collapses are something we derive rather than something we postulate in Bohmian mechanics. So the conditional wave function of particle 1 collapses to either the ground state or the first excited state. And as we talked about before, both of these possibilities imply that particle 1 will be at rest. However you think about it, though, the crucial point is that by measuring the energy of, or by intervening in the affairs of particle 2, which remember is, say, 1,000,000 miles to the right, we have caused a sudden and dramatic change in the behavior of particle 1, which remember is 1,000,000 miles to the left. It went from oscillating back and forth to just sitting there at rest. We made it stop moving instantaneously from 2,000,000 miles away. It is a truly blatant case of spooky action at a distance, which seems impossible to reconcile with the relativistic concept of locality, according to which all causal influences propagate at or below the speed of light. Then he says one has to remember that, although according to the pilot wave theory, particle 1 is initially oscillating back and forth, one cannot observe this motion or its subsequent cessation. Or rather, if you did try to observe it, this observation would require interacting with particle 1 with some physical observation equipment, which would disrupt the subsequent evolution and break the entanglement with particle 2, just like the energy measurement in the above example does, and hence imply that a later measurement of particle 2 has no effect whatsoever on particle 1. All right, so what exactly is this conditional wave function that can undergo this collapse here? So Travis Norson says in this 2016 paper, so consider, for example, a particular particle with degree of freedom x. We can divide the generic configuration space, so x and y here, where y now denotes the coordinates of other particles. So degrees of freedom from outside our subsystem of interest. And so he's talking about how there is sort of a universal wave function, and then when we sort of arbitrarily split it into the system that we're interested in and then the rest of the system, we can look at the system of interest as the conditional wave function. And as we'll see, it's sort of conditioned on the positions of all other particles. So we then define the conditional wave function, or CWF, for a particle as follows. And so this is our wave function here, or this is the conditional wave function here. And we see that this depends on sort of the position of all the other particles. So we're evaluating it with sort of all the other particles right here. So with our y being all the other particles. So that is the CWF, the conditional wave function for one particle, is simply the universal wave function evaluated at the actual positions of the other particles. Note that the guidance equation, according to which the wave function orchestrates the motion of the particles, for each particle can be re-expressed in terms of the particle's conditional wave function, so that the conditional wave function can be understood as having precisely the dynamical significance for the associated particle that one perhaps normally imagines to be involved in a pilot wave theory. It is fairly straightforward to see that in the case where the particle in question is suitably decoupled from its environment, so if we're looking at an isolated subsystem, the associated conditional wave function will obey the obvious single particle Schrodinger equation that one would have expected from the point of view of textbook quantum mechanics. And so he's saying that if we do have a suitably isolated system that we are working on, then we can sort of consider the conditional wave function just the normal wave function of a single particle. The more interesting and surprising thing is that in the kind of case that we would normally describe as a measurement, the conditional wave function collapses according to the usual textbook rule, even though nothing like a collapse postulate appears in the basic axioms of the theory. So what's simply, it's called conditional because just like in a conditional probability, we're essentially saying the wave function of a system X given the wave function of everything else Y, which we could perhaps denote similar to a conditional probability like this as being kind of like this. So it's the wave function for X given the sort of wave function of all particles at other positions Y, where Y always evolves according to the universal wave function, but X can collapse similarly to textbook quantum mechanics. And so Norson says of this collapse of the conditional wave function, so again, this is from this 2016 paper here. So consider the time evolution of the conditional wave function of the particle in the box. At t equals 0, when the quantum state factorizes, the conditional wave function is just proportional to the energy superposed initial state of the particle. And so we're looking at this figure again. He's going to be talking about this figure again. And so we're looking at sort of these islands here before they have separated from each other. And that's what he's talking about here, these energy superposed initial state of the particle. And so, yeah, right here, he's showing that it's a superposition of them. Then, as the quantum state begins to separate into branches, the conditional wave function evolves in a very complicated, nonlinear way. And so that's why we end up with this weird path that the particle takes through configuration space. But once the branches have ceased to overlap appreciably in configuration space, so the left on figure 4, which is what's shown right here, the conditional wave function settles down into one of the energy eigenstates. For example, for the particular initial particle position illustrated in the figure, with the final pointer position y of t in the support of n equals 2. And so this one, so we see the particle stops right here in configuration space, which corresponds to this energy eigenstate in this configuration space. And the support for n equals 2, so n equals 2 just being this first excited state here. It is clear that we have this, so again, it's just talking about this right here. So the conditional wave function has collapsed as a result of the interaction with the energy measuring device from a superposition of many energy eigenstates. Because remember, it's the interaction with the device that causes this to separate into these energy eigenstates. They were in that superposition before the measurement. So from a superposition of many energy eigenstates to the one particular energy eigenstate that corresponds to the actual outcome of the experiment. This is the sense in which the pilot wave theory explains the collapse postulate, and in general, the rules that are instead postulates of ordinary quantum mechanics. Although, according to the pilot wave theory, the big, i.e. universal wave function always evolves according to the Schrödinger equation and hence never collapses, the small wave function, so the conditional wave function associated with subsystems obey a subsystem Schrödinger equation when, according to ordinary quantum mechanics, they should, but also collapse it when, according to ordinary quantum mechanics, they should. So this is just that same figure I showed above. But yeah, he's saying that we can derive this collapse thing going on for a conditional wave function rather than just postulate it, and that the collapse will behave exactly the same way as we get in textbook quantum mechanics. But anyway, that was everything I wanted to talk about in this video. Again, the overall thing to take home from this is that Norson here is showing that Bohmian mechanics is both contextual and non-local, which are two things that have to be true of at least a hidden variable quantum mechanics theory. I guess any quantum mechanics theory would have to be both contextual and non-local. But what we want to show with Bohmian mechanics, which is a hidden variables theory, is that it too is contextual and non-local, which are kind of two things you wouldn't expect from a hidden variable theory, but we know from the Kochen-Specker theorem and from Bell's theorem that we need our quantum mechanics theory to be both contextual and non-local. But anyway, I hope you found this video helpful. So making these videos can be kind of time consuming, and I do, have an actual job. So I have started a Patreon if you wanted to, toss a few bucks my way. If maybe you find these videos helpful in any way or interesting in any way. Obviously there is no pressure to do that, but if you wanted to, you could. But anyway, I will see you in the next video.